All right, ladies and gentlemen, we are going to start our unit on something called scientific notation. Today's lesson is really an introduction to what scientific notation is, and you have to really understand scientific notation in order to be able to do anything else for the rest of this unit. So this video will really set the foundation for you, okay? So what's the point of even using scientific notation? The reason why we use scientific notation is to express very large or very small numbers. So we're talking about large as in the distance from here to the sun. That's an extremely large number, right? Or small as in the weight of an atom, okay? So these are some examples of numbers that would be measured in scientific notation. But really, any number can be written in scientific notation by expressing it in two parts. A coefficient. Remember, coefficients are just numbers in front of variables, okay? So a coefficient with where a is between 1 and 10. So I need you guys to write down that a has to be between 1 and 10. That's what this expression right here means. It can be 1, but it can't be 10. And then a power of 10 where the exponent is an integer. And that is key, that the exponent is an integer, okay? So here's the thing, this a value, this coefficient has to be between 1 and 10. So let me write you an example of a number that's written in scientific notation. An example would be like 5.7 times 10 to the 8th power, okay? This is written in scientific notation where the coefficient is a, which is 5.7, and the power of 10 is my integer, which is 8, okay? Another example would be 2.35 times 10 to the negative 4th power, okay? All right, so now it says tell whether each number is written in scientific notation. If it is incorrectly written, state the reason, okay? So number 1, a horse chestnut has a diameter of 2 times 10 to the 0th centimeters. So the first question you gotta ask yourself is, what's my coefficient? Well, the coefficient is 2, okay? Now, is the coefficient between 1 and 10? It absolutely is, so that works. And then you have to ask yourself, is my exponent a power where the number is an integer? And yes, it is. So this is written correctly, okay? So this one will work for us. All right, so now let's look at number 2. Neptune is about 4.488 times 10 to the 9th kilometers from the sun. Now it's going to mean that the answer is going to be really, really, really far, okay? And that makes sense because you're multiplying by 10 repeatedly. And we'll talk a little bit more how to figure out these actual numbers, okay? So right here is my coefficient between 1 and 10. 4.488 definitely is between 1 and 10. And then is my exponent an integer? Yes, it is. So this answer is also written correctly in scientific notation, okay? So we'll say that this is also written correctly. So then let's look at number 3. The approximate wavelength of infrared light is 0.01 times 10 to the negative 5th power. So for this question right here, my coefficient is 0.01 and my exponent is negative 5. My exponent is okay because it's an integer, but my coefficient is not good because it's not between 1 and 10, right? It's too small. So what we'll say here is no, because the coefficient is too small. It's less than 1. All right, and then lastly, let's look at number 4. A football field, excluding zones, is 10 times 10 to the 1st yards long. So we have to look at our coefficient. Now this right here, the answer is 10, or the coefficient is 10, but if you look right here, what it says here, this number means that a cannot be equal to 10. Remember this right here, you can't have 10 as the actual value. So this right here, it doesn't work because the coefficient is too large. So I know we have questions 5 through 8 to do here, but we're going to actually skip those for right now. And then we're going to go to questions 9 through 12. So these directions tell us to write each number in standard form. So I want to figure out what this number is written as an actual number itself. Now, this is written in scientific notation because this number is between 1 and 10, and you have an exponent that is an integer. So what I'm going to do is I'm going to write this out so I understand it better. 7.1 times 10 to the third power means 7.1 times, this right here is 10 times 10 times 10. Okay, now you should be able to figure out what 10 times 10 times 10 is. Hopefully you know that 10 times 10 is 100, and then 100 times 10 is 1,000. So this ends up being 7.1 times 1,000. Okay, so if you've got 7 sets of 1,000, it's going to be 7,000, and then this right here is 0.1 of 1,000, so it's 7,100. Okay, so let's try the next one, number 11. Number 11 says 9 times 10 to the fourth power. Okay, so what I'm going to do is I'm going to take 9 and I'm going to multiply it by 4 sets of 10 this time. So 10 times 10 times 10 times 10. So we know that 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is going to be 10,000, right? So, and this should make sense too right here. 10 squared is 100, 10 cubed. You just keep adding zeros on, right, when you're multiplying it out. So this is 10,000. So you'll end up getting 9 times 10,000, which means you've got 9 sets of 10,000, so your answer is 90,000. Okay? There's a shortcut for this, but I don't want to talk about it quite yet. You will learn it, but we're not going to talk about it quite yet, okay? Now let's look at number 10. Number 10 is a little bit trickier. So in number 10, you have 8.12 times 10 to the negative third power. But remember, when you have a negative exponent, it means you have to do the reciprocal. So it's really 1 over 10 to the third power, okay? So then I end up getting 8.12 times 1 over 1,000, okay? And then I can technically put this over 1 so I can multiply my fractions together. So I end up getting 8.12 over 1,000. So this means that my answer is going to be 8 thousandths, okay? Plus another little bit added on to it. So remember, this right here is a tenth, okay? If you have 0.01, you have a hundredth. So if you have 0.001, you have a thousandth. So that means that this answer right here is going to be 0.00, it's not 1,000th, it's 8 thousandths, 8, and then the 1, 2 tags along. Okay? And then lastly, let's look at this one right here. This one right here is going to say 2.5 times 10 to the negative second power. This becomes 1 over 10 to the positive second power. So you get 2.5 times 1 over 100. Again, make this denominator be 1. So you end up getting 2.5 out of 100. So it means you've got 2.5 hundredths, okay? And here's your hundredths place. So you get, instead of 0.01, you get 0.02, and then the 5 just gets to tag along, okay? All right, we're going to skip back to question number 5, which is on the front of your paper. This time what we're going to do is we are going to take the numbers that we have and put them in scientific notation. So the first thing you need to look at is what the leading number is in your term, in your number. So the leading number here is 4. So this is the hundreds place, right? And if you remember, when we talked about this earlier, this coefficient, this a value, has to be between 1 and 10, okay? It cannot be any less than 1 or any more than 10. So what I'm going to do is I'm going to move my decimal place so that it is between 1 and 10. So it's going to say 4.277. I'm allowed to move the decimal place as long as I multiply by a number that will give me an answer that's equal to this number right here. Now remember, this digit right here is going to tell you what you have to multiply by. See how this is 427.7? It means you have to multiply by 100. And hopefully it makes sense to you that 4.277 times 100 would give you 427.7, okay? Now remember, we said that 10 to the first power is 10. We said 10 to the second power is 100. 10 to the third power is 1,000. 10 to the fourth power is 10,000, so on and so forth, right? So if I'm multiplying by 100, it's 10 to the second power right here. So it really means what I'm doing is 4.27. I'm multiplying by 10 2 times. And that should make sense to you because 10 times 10 is 100. 100 times 4.277 is 427.7, okay? We're going to skip to number 7. We're going to try this one together. So I need to move my decimal place so that my number is between 1 and 10. So I want to put it after the 8 because now I have 8.5621. This number is between 1 and 10. So now you have to ask yourself, what digit is this 8? Well, this number is 8,562.1. So you have to multiply this by 1,000 because it was 8,000, right? So 1,000 is 10 to the third power. So my answer is 8.5621 times 10 to the third power. Okay? Number 6, though, is a little bit trickier. So in number 6, this time this number is too small. In these examples, the numbers were too big. So I need to move my decimal place so that my number is between 1 and 10. So I could move it all the way to the end, and I end up getting 7. Is 7 between 1 and 10? Absolutely, right? So I multiply 7 by, this right here is the tenths place, this is the hundredths place, this is the thousandths place. So I'm multiplying it by 0.001. Or you could just say you're multiplying it by 1 over 1,000 because you said that this is the thousandths place, right? But 7 times 1 over 1,000 means it's going to be 7 times 1 over 10 to the third power because we figured out that 1,000 is 10 to the third power. But when we write our answers can't have fractions in them. So the last thing I'm going to do is I'm just going to say it's 7 times 10. In order to get this out of the fraction, it means that the exponent was originally negative, so it's 10 to the negative third power. Okay? All right, we're going to try one more together, and again, we'll get a lot more practice with this in class. So 0.06. I want to move my number over so that my number is between 1 and 10, my coefficient. So if I end up getting a 6 here, I could say it's 6 times, this is the tenths place, this is the hundredths place. So 6 times 0.01. Okay? So then when I go ahead and do that, I end up really getting 6 times, since this is the hundredths place, it's out of 100. So 6 times 1 over 100. Or really, 6 times 1 over 100 is 10 squared, right? So I end up getting 6 times 10 to the negative second power. And then that's my final answer for that question. Okay, sorry to be skipping around. We're going to go back to question 13 now. And the directions say to identify the greater number in each pair of numbers and then to justify your reasoning. So in question 13, you have 5.6 times 10 to the second power, right? So you have 5.6 times 10 times 10, right? And then here 2.1 is being multiplied by 10 3 times. So which number would be bigger, the number where I multiply by 10 twice or the number where I multiply by 10 3 times? It should make sense to you that this number right here is going to be the larger number. So we would say 2.1 times 10 to the third power is larger because you're multiplying by more tens. Okay, so now let's look at question number 14. Number 14 says 3.4 times 10 to the negative first power, which means you're going to multiply by 1/10, right? Because you got to do the reciprocal, 1 over 10 to the first power. And then this number right here is 1.1 times 1 over 10 to the first power, okay? So if you notice, you're multiplying by the same number here. which means that it's not going to be based on the exponent to figure out which number is larger, because the exponents are the same. It's going to be based on my coefficients. So in this example, my coefficient for the 3.4 is larger. So that means that 3.4 times 10 to the negative first power is larger because the exponents are the same for both expressions, but the coefficient of this expression is larger. So you always want to look at the exponents first, and then if the exponents are the same, then you start looking at the coefficient. All right. I know this might seem kind of weird to you, but we will get a lot more practice with all of this stuff, and then you will be in great shape with this stuff if you work hard. All right. See you in class.